Hey everyone, thank you for coming. My name is Josh, and I'm a technical artist at SideFX. This talk is going to be all about walking you through the machine learning process in Houdini, and I'll be explaining some of the more important and foundational machine learning concepts for anyone if you're wanting to get started with machine learning in Houdini. And now this is assuming that you either know very little or nothing at all about machine learning. And hopefully by the end of this presentation, you'll have a better understanding of all the various ML nodes Houdini has to offer, and you'll be able to use those to hopefully train your own machine learning models in Houdini with little to no code whatsoever. So to get started, what actually is machine learning and how does it work? Machine learning is a way of teaching a computer to learn from data rather than explicitly programming a specific task to be done. What do I mean by that? Well, instead of writing a set of fixed rules or instructions for a computer to follow, it will instead look at data or examples that we give it, and it will then figure out the different patterns and relationships to make predictions and decisions on new data. And now there are a few main steps in the machine learning process, and the first one that you're always going to start with is data collection. This is, in my opinion, the most important step of the machine learning process. If you don't have good data, you're just not going to get very good results. And it's like the same with FX simulations in Houdini. Let's say, for example, you're making an explosion and you don't have a very good source that you're emitting from, then you're probably not going to get the best result. And let's say instead you spend some time making a nice explosion emitter, you put that through a Pyro solver, you're probably going to get a much nicer explosion. And it's kind of the same idea with this. You really need good, high quality data. And most importantly, you need lots of it. So then step two, after we have all of the necessary data, we need to train a model. And what this means is we're feeding our data into some sort of mathematical algorithm. And this algorithm is then finding patterns in the data set and learns from it. And then step three, the third and final step, is once the model's been trained, we're going to use it to make some sort of predictions. And the fancy word for this whole process is called inference. Inference is the process of analyzing new, unseen data and making predictions based on what the model learned during its training process. And so to kind of put this all together, we first need data. We then take that data and we give it to some sort of algorithm, which will then detect all the different patterns in the data set. And then this gives us a trained machine learning model. We can then take that model, give it new data, and then it will make predictions on that data. And this is called inferred data. And to demonstrate and further explain kind of this whole ML process that I've been talking about, I'm going to be taking one of our machine learning examples and kind of reverse engineer it a little bit. And hopefully by doing this, you'll get a better understanding of how machine learning works in Houdini, and you'll be able to use this as a foundation for your own ML setups. But before I do that, I want to quickly go over some important and commonly used terms just throughout machine learning. And you'll see some of these a lot in some of the Houdini ML nodes as well, so it's good to know. First up is inference. I know I just touched on this, but it's really important, so I'm going to do it again. Inference is the process of using a trained model to generate predictions on new data that the computer has never seen before. There's multiple ways that this can be done in Houdini, but the easiest is probably through the use of this Onyx inference node. And as you can see, there's two different versions. There's one for SOPs and one for COPs. So you can run inference on 2D data, 3D data, or volumetric data as well, as long as it's a Houdini volume. VDBs, at least as of right now, are not currently supported. And then that brings me to the second term, which is ONNX. That last node is called Onyx Inference. We now know what inference is, but what is ONNX? And ONNX stands for Open Neural Network Exchange. And it's a format built to represent machine learning models and use them at runtime through the inference process. I should also note that ONNX is a standardized format, which means that you can take any ONNX file you find, regardless of the environment it was in, and you can use it directly in Houdini, which is really cool. Next up, we have supervised learning. And supervised learning it's currently what Houdini uses for its machine learning model training. And it's an approach in machine learning where a model is trained using labeled examples. And a labeled example includes two things. It needs input data, and it needs the correct output data. One way you can think about this is, say you have a student who's solving a math problem, and they got a solution to that problem, but they're not sure if it's correct or not. They can then go and look at the answer provided by the teacher. And you know that the teacher's answer is correct. And by comparing the student's answer to the teacher's answer, you know if the math problem was solved correctly or not. And this is the way that the machine learning model learns what's correct and incorrect data throughout the training process. And then finally, the last term I'm going to throw at you today, I know it's a lot, is principal component analysis, or PCA for short. And PCA it's a technique that reduces a large set of variables, or just a large data set, let's say, into a smaller set of key patterns, which really captures the most important information of that larger data set. And this helps simplify the data set while still keeping its essential structure. Another way you can think about this is think of PCA like you have a complex painting, and you then reduce it down into its essential shapes and colors, so you can work with a more simplified version, but that simplified version still captures the overall look and feel of the original. This is essentially what PCA is doing, just with numerical values instead. So now it's time to go and start reverse engineering our machine learning example and kind of see how this entire ML process works inside of Houdini. And this is the muscle deformer example. Some of you may have seen it. And I'll be using this throughout the rest of my presentation today. And you can find this on our content library on SideFX.com. I'm not going to be walking fully through this file node by node. That would take a really long time. This is more so going to be explaining how the overall machine learning process works in a file like this. So you can go ahead, download it, and kind of look through it on your own time and really understand what's happening. And again, use it as a foundation to further your own machine learning setups in Houdini. So when you first download this project, you'll see it comes with two different HIVE files. And there's one that trains the machine learning model and another that uses that trained model on a rigged character, the same way you would in production. So let's first start by taking a look at the final result and see what this ML muscle deformer actually does. So here you can see I just opened up the file and quickly posed the character. And when I toggle between this ML skin deform, you can see the difference of what the character looks like with the muscle deformation and without it. And in this example here, it's quite a significant difference. And then when I go and I click on this ML skin deform, you can actually see there's one parameter inside of it, and it's reading an Onyx file, which is being read from disk. And inside this HDA, that Onyx model is then performing inference on the data that we give it from our character as we move it around. And that's what's giving us that nice muscle deformation. So I know everything up to this point is probably pretty self-explanatory. The last two things were just two steps, but just a quick recap of everything that we've got going on so far. First, we have an Onyx model that's being read somewhere from disk, and this is inferring data. The result of the inference process is then being applied to the character as it gets moved around, and that's giving us the deforming muscles. So in our three-step machine learning process that I went over before, the third step, model inference, we can kind of check off. We've done it. We have our Onyx model, we've inferred it, and it's giving us the desired result. So now the question is, how do we actually create it? To do that, I'm going to be going into the other Houdini file. It's called train.hip with this specific project, which is where everything is actually happening when it comes to the creation of this Onyx file. And when you open it up, you'll see there's a top network. And when you go inside the top network, you'll see there's kind of a lot happening here. But because I'm reverse engineering this project, I'm going to start from the bottom and work my way to the top, because a lot of this is actually just automation and not actually needed for the whole ML process in Houdini. So at the very bottom of this top net, there's a node called ML regression train. And if you remember, again, the ML learning process, step 2 is model training. And that's exactly what this node does. First, it takes a data set that you find that's being read somewhere on disk. It will, using a Python virtual environment node, install PyTorch in the background, and then it will train that data set with PyTorch. And then once the training is finished, it's going to output an Onyx file. And all of this is happening without the user needing to write any code whatsoever, which is really nice. And so, okay, now we know where this Onyx file is coming from that was being used for inference earlier in that rigged character. And it's the output of this ML regression train top. But in order to get this output, this node needs some sort of input. What kind of data is that input exactly looking for? If you go back and look at the ML regression train top, it's part of a collection of example-based machine learning nodes in Houdini. And if we go up the chain a little bit, in this top network, you'll see that there's a ROP fetch node. It's called a fetch dataset. And this fetch node is referencing another node, as you can see. That's ROP path parameter, and it's called ML example output. This ML example node it's what's exporting the dataset that is used for the model during training. And so, okay, one more recap. I know I want to make sure all of you are still here and following along. Now we have a few more steps. There's an ML example output node, which is writing our data set out to disk. That data set is being trained using this node in a top network. And once the training has finished, we get our Onyx model. We then can take that model and we can really do anything with it, but here we're feeding it through the inference process, and the result of that is being applied to the character, resulting in muscle deformation. So now everything up to this point, this entire process that you see here with the different ML example nodes, you can use this pipeline to really train whatever you want, whatever type of ML model you want, as long as it works within this pipeline. None of this is specific to this muscle deformer example yet. That's our last question, isn't it? What goes into the ML example output node? This is our real data set that we're going to be making. And this node expects a set of individual ML examples, each of which in Houdini are packed primitives. And again, going back to our supervised learning definition from earlier, if you remember, an example consists of two things. First, it needs input data, and then second, it needs the correct output data. And the way that we do this inside of Houdini is with this ML example node. It's very convenient. And the first input of this node is our input data that we want to use for training. And then the second input is the correct output data that's associated with that input data. So now, with all this in mind, what I'm going to do is kind of walk through the whole muscle deformer example from start to finish and just do a really broad overview of what the entire setup is like with our data set, with making our data set from start to finish. So as we know, the first thing we always need is we need data. We need to collect data or make data. And all the data that's created in Houdini for this project is by first creating a lot of random poses for the character. The idea is we want a large data set of deformed muscles, and that's what we're going to use to train our machine learning model. So, and you can do this really easily in Houdini using this ML pose generate node, and can generate as many poses as you want. And so now, in this example, we have 16,000 different poses. And for each one of these generated poses, we're going to generate a tetrahedral mesh, which is then created and run through a quasi-static simulation. And all that means, it's a bunch of fancy words, but let's say you have a character in its rest position in like a T-pose, and then you have your goal pose, and then all it's doing is it's going to move from its rest position slowly to the goal pose, and it's going to do that, and it's going to simulate the muscles on the surface. So now we can go back to our ML example. We can say, okay, our input is going to be the character skeleton, the posed character skeleton, because this is what we want to give to our trained model. We want to give it a posed skeleton, and in return, we want the simulated character mesh to actually get our muscle deformation. But if we do this, there's going to be a slight issue, and that issue is that the point count on the original character mesh isn't the same as the point count on the simulated mesh. And to fix this, the original character mesh just has to be point deformed to match the position of the simulated character mesh. It's a pretty simple fix. And once we do that, we can then take the new correct data output, the second input of this ML example node. That's what's going to be the deformed original character mesh that we just did. And once that's all done, we technically have our ML example ready to go. However, if we were to run all the points on this character times 16,000, that's because 16,000 is how many poses we have. That's going to be a lot of data, and it's going to be really, really slow to train our model. So there's a few ways we can avoid this. We can first optimize the training data by first extracting only the points for the ML training that are necessary. And this is done by taking the mesh that was deformed from our simulation and subtracting it from the mesh that was deformed from just our character pose. And what this does, or what this gives us, is just a bunch of displaced points in 3D space. And these points are the only points that were used in the actual muscle simulation. And now, I'm not going to go too much into this part because it's a whole setup, but the idea is here to further optimize this from millions of points to just the only points that we really need is we take these points and we run it through PCA, Principal Component Analysis, for further optimization. And then those final points that were the result of the PCA is what we're going to put into the second input of our ML example. And then as well, there's also one other thing that I changed on here as well. If you look, the first input can't be just our posed character. It has to be serialized. And this can be easily done with, there's an ML pose serialized that will just take the input of a character, it will serialize it specifically so you can give it to this ML example. And then finally, just like before, we have the output of our ML example that's written to disk with the ML example output node. And this is what writes out our complete data set that's going to be used for training. This data set then will get imported into TOPS with this ML regression train node. And then once the training is finished, it will give us our trained model that we can then use. That model, once more, is going to be run through the inference process. And the result of that is going to be the character that's giving us the muscle deformation. That's all I've got for you today. If you're interested in learning more about this whole machine learning process in Houdini, this is a very broad overview. Definitely check out the examples on the content library and go through them. You're definitely going to learn a lot. Thank you.
Hello. Are there any other use cases that come to mind for machine learning and Houdini aside from muscle deformation?
So yeah, one thing you could do is you could take this exact same setup, for example, and use it for any sort of character-based effects. If you want to do this with clothing for real-time clothing simulations in games, let's say, you could do that. You could do it through hair. There's another, on the content library, there's a groom deform example that uses a very similar process, but you get a different result. The one thing you really just need to change is what your input data is going to be. So instead of a muscle simulation, you're going to give it a bunch of different guide grooms and stuff like that.
Very cool.
Hey, I basically asked the same question, but just push it a little bit further. Do you ever see a possibility in training like a better looking Pyro or like a fluid sim? Like, more points?
I'm not sure what I can tell you about that. So,
it's like kind of far away in the future, or is?
I think it's a lot closer than you think.
Oh, I see. The other.
Any other questions?
You mentioned how like Onyx is a standardized system. So is there ways that you can like export the skinning into Unreal or Maya, like for a rig or for a game, like you mentioned?
Yeah, so I don't know. I'm sure you're aware. There's also a ML deformation model for Unreal as well. And if I remember correctly, a lot of that was actually done in Houdini just because it's really good at handling large amounts of data. And you can, it's, as I said before, you can just take any Onyx model that you find even online really. And because that's your model, you're running the same inference process on it, whether it's in Houdini or in a different application. So you should be able to do that. Yeah.
Hey, so how much data would you say is necessary to get like a really reliable muscle deformation? And like, have you considered exploring like synthetic data, stuff like that to get like a lot of data that you really need?
Yeah, so I'd say for this example in particular, 16,000 poses or, different muscle simulations is what was used. And that's kind of a good balance between speed and quality. Obviously, the more data you have, the better, but that's just going to grow exponentially when it comes to actually training your model. If you have too little data, you're not going to get a very good result either. As for synthetic data, we are exploring different ways of doing different types of ML. I don't know if you've seen, but there's a few different talks that you can find online right now where there's people who have actually used Houdini and used similar processes in Houdini to do like computer vision training and generating synthetic data for other applications in machine learning. And that's definitely something that there's going to be more of that to come.
Awesome. Thank you.
In the slideshow, I saw that for your Onyx file, it was around like 20 gigabytes. Is that like even after the optimization with the principal component analysis? I was just wondering for like the delivery and like exchange of Onyx files for like, I can see it being exchanged like HDAs, like if someone trains something. Is it generally like that large with such a large data set even after optimization, or are there ways to reduce it just to get like delivery and exchange more efficient, I guess?
Yeah, again, a lot of this varies on the type of model you're doing, how much data you have, what that data is. So I'm not sure if I have like a precise yes or no answer for you, but it really does depend just on a bunch of multiple factors. There are other ways, other techniques that I'm sure you could kind of reduce that down more if you wanted to. But in this example, that was the final trained model, and the PCA part was to kind of optimize the data set that you're going to feed into the model to train it.
Any more questions?
So in the example you showed, your output was essentially probably a bunch of point data that's driving vertices.
Are you able to define what the output is? Could you, like, for example, I'm interested in building a system that takes in arbitrary points in space and tags them. Could you build an ML model that looks at, say, for example, an armature and then figures out what each point is and returns like name attributes?
Could you repeat the last part one more time?
Like, can you define your outputs? Like, right, you're outputting a bunch of points in space and moving, changing the original mesh. But can you also build an ML model that can output like name tags on an armature, for example? Could you do other things and then just move points?
Yeah. So again, there's a few different approaches to machine learning. The specific approach that was done here isn't really for, I'm not sure if this is what you were asking or not, but anything in the realm of computer vision or stuff like that, you would take a completely different approach to doing something like that. As for the actual output and defining the output, the result here that you saw in the final result is points, but that's really on the points, you kind of have your different data and, attributes, and that's really what that's what's being used to do your final training. So I guess when it comes to actually defining what that data is, that comes down to, okay, what kind of model do you want to train? What kind of simulations are you going to run? Are you going to run simulations? Stuff like that.
Thank you.
You mentioned that the input data on the ML example node needed to be serialized with like the built-in ML pose serialized node. I was wondering for like other applications, just because in this one it was like you have the built-in node for the example file for serializing poses. I guess more of like what is serializing and how would you do that for like any type of input data?
So that I could not tell you right off the top of my head, but I do know that it is documented. So if you were to go and look it up, read through some of the ML documentation, it does kind of explain that further in there.
Any last questions?
Form seem very arbitrary. Is symmetry used in any kind of accounts? Does a left bicep move same as a right bicep would?
There's a few different ways of generating all those poses. One thing that you want to do is add joint limitations to a lot of stuff, but I don't think it's really the more data that you have that will kind of get evened out over time, I believe. To my knowledge, symmetry isn't that big of an issue. If you have tons of different poses and you have a big enough data set, you should be fine.
It just seemed that if you, as opposed to 16,000 poses, you can cut that down and basically just mirror your data if you had a symmetrical low-res mesh, cage mesh. Or is that naive to think?
I would think that
it is naive, you're being polite.
I don't know.
Is there like it from the muscle deforming example? It seems like this would be good in any case where you don't need like exactly precise muscle deformation. Are there downsides you've noticed to working with these machine learning models?
There's a time and place to use, obviously, stuff like this, but I'd say the big thing, if you really dedicate the time up front to, generating all the data, training a model, then actually using that model and getting that muscle deformation, it's really, really fast. Same with, there's another example that I saw that was doing this, but with clothing and clothing deformation. If you were to do that, then you essentially have like a real-time cloth simulation, but you're not actually simulating it, you're just deforming it with a machine learning model.
One more in the back there.
For the like Onyx inferencing, I'm just wondering, like, just I don't have a use case in mind, but for in this case, what it's like outputting is deformation on pre-existing points. Is there a limitation to the kind of thing that can be inferred? Like, for example, does it have to? Would a possible output be like the creation of new geometry, or can it only output like adjustments to attributes on existing geometry, I guess? Or is it able to just like, it can just output no matter like?
It's more so you're inputting data into it. It's inferring that data, and then you get data as a result. So you're still getting the points, but then you take the data on those points, and then you kind of do the reverse process of what you did with the whole principal component analysis aspect of it. And then you can apply that data or reapply that data to your character. It's not actually giving you the final result straight away.
Okay, thank you.
Okay, thank you so much, Josh.